Are they not on the website? Okay, I'm sorry. They will be up soon. We had to finalize these a little bit late today, so they might just not have gotten a chance to, but they'll be up as soon as they can. Okay, so what did we talk about yesterday? Or not yesterday, Monday. So we basically spoke about query optimization, and particularly we went over, the equivalency between relational algebra and the tree, the relational algebra tree that would kind of represent a query. And we talked a little bit about how you could reorder operations to make them a little bit more efficient, et cetera, et cetera. Today we're going to be touching on a little bit more of the actual algorithm itself behind query optimization. And in particular, we'll be touching upon concepts like dynamic programming, but not in the 170 way. It'll be much more intuitive than that. 170 is a great class. It's just the first time you see dynamic programming in it, a lot of the time you're like, what the heck is this? So, I don't know, maybe you guys are smarter than me. First time I saw it, I was like, what? So, what are we actually given? And I think it's important to step back, and before we try to tackle this problem, let's try to understand what we're given and what we need. Okay, so we have a closed set of operators. Basically, we have relational operators and physical implementations. Concretely, what do we need to actually look at? We need to first look at the plan space. Okay, what plans are we going to consider? What plans are valid? What are we going to consider? We're going to have to estimate the cost of different query plans. We need to estimate the cost of joins, of scans, of query plans. And to do that, we need to apply certain cost formulas and assumptions. And in order for that to happen, we need to have certain information about the tables themselves. So you may remember from last lecture, we had this thing called a catalog manager that stored a whole bunch of information about the table. We're going to be referencing that heavily today. Why? Because if I tell you to join sailors and reserves, if you need to estimate the cost for it, it's physically impossible to do it without actually knowing some sense of the size of the tables. Lastly, we're going to also need to use a search algorithm. And this is because the plan space is very, very big. If I ask you to join 4 tables, I mean, without even considering the different types of joins that you could use, you could order those 4 tables in any which way in the join, right? A join B join C join D, or D join B join A join C, et cetera. How do you know which one to use? So we need a way to prune that plan space, that search space. So we're going to need to use a search algorithm for it. We can't just consider every little thing. We have to be a little bit smarter than that. So we're going to be considering the System R optimizer today. It's a very comprehensive framework, and it's been refined and reused and tweaked over time. And people are still improving it because it is by no means perfect. There are some significant weak points, as with anything with this. But it's very good for what we have. And this algorithm that we're going to be using, this optimizer, System R optimizer, really works well for about 10 to 15 joins. After that, you start running into some problems. After that, it just becomes way too big or way too costly for you to use this optimizer. But for about 10 to 15 joins, this works really well. Okay, and we need to think about a few things. Like I said, firstly, the plan space is very large, and so we need to prune it. And so we can maybe think about something a little bit intuitive, which is that if I'm trying to join A, B, C, and D, what if I just said, okay, let's just join D to the set of A, B, and C. And let me find the most intuitive way, the most efficient way to join A, B, and C. And then I'll just join D to that. Or I could join A, B, and D together. What's the most efficient way to join A, B, and D? Then I'll just join C to that. So basically the idea is, if you're trying to join n tables together, maybe just first say, okay, assume I have n minus 1 tables already joined together. What's the most efficient way to, what's the most efficient set of n minus 1 that I can then join this nth table on, in a sense? And that's the idea of dynamic programming here. You're using the results of previous subproblems in your query, in your algorithm, to actually execute this new iteration. And if none of that makes sense, don't worry. We're going to go over it in detail. I'm just trying to give an overview of what we're going to talk about. And then, like I said, we need to do cost estimation, because that's really at the core of all of this. You can't actually estimate the cost of joins without having some way to have a heuristic of sorts for selectivity. For example, if there are 10 unique values, and I'm trying to pick one value out of it, what percent of the table am I going to select? The intuitive answer is 1/10. But what if that value isn't uniformly distributed? What if that data isn't uniformly distributed? So these are things we might need to consider. So for all of that, we need to use a technique of cost estimation. Let's first talk about the plan space for QO. Okay? And going to be blunt, some of the parts here, if they're too boring, stop me and we'll try to figure out a way to make them a little bit more exciting, because I think this can get a little bit dry at times, and I've tried my best to spruce it up a little, but if you guys find that you'd like it presented in a different way, just let me know. So our units of optimization are query blocks, okay? And what that really means is, let's break our query up into blocks and optimize one block at a time. So let's take an example where you have a subquery. What you could do then is first see, is it a correlated or uncorrelated subquery? Does anyone remember what correlated and uncorrelated subqueries mean from the first couple of lectures? Okay, that's all right. Correlated queries and uncorrelated queries, basically if I have a subquery and it doesn't reference any of the aliases in the outer query, it's uncorrelated. I don't need to compute it every iteration for every single row. I can just compute it once, and then I have it good to go. Correlated subqueries, you can imagine, have correlation with the outer block. That is to say, the subquery actually references something from the outside, from the outer query. So we need to decide, we need to first check, is it an uncorrelated block or a correlated block? If it's uncorrelated, you can just compute it once, materialize the result, and then use that for whatever you're going to do. If it's correlated, you might have to really try to disentangle it, flatten it. You can decorrelate nested blocks, but that's kind of outside the scope of this class, so we'll skip beyond that. But all of this is just to say that what we're trying to optimize are queries, okay, and query blocks specifically. So you're going to break your query into blocks, your subqueries, et cetera, and you're going to try to work with that. Now for each block, what are we going to consider? We're going to consider plans that have all of the relevant access methods from every single table in the from clause. Okay? So I think the best way to think about this is there's like it's a left deep join tree. And what I mean by that is, if you look at the structure here, it's not bushy. It's a spindly tree in a sense. Does everyone kind of see that? It's a spindly tree. It goes kind of to the left, and then at every single iteration there's one branch sticking out for the right, that tree that you're going to join. So here, for example, you're going to have A join B. That result is going to get joined onto C, and that result is going to get joined onto D. And what that actually means is basically at any given time, you're only joining one table on to a set of n minus 1 tables. What that is to say, if that sounds a little bit confusing, let's simplify it a little bit. Let's think of it like this. If you're going to draw your join tree out to describe how the joins are computed, you're only going to have base tables, tables in the from clause on the right. And any of the rightmost branches, there'll only be tables in the from clause. And another good way to think of it is you're never going to join something like this, A join B, join C join D. That's never going to happen. You're always going to add on one table at a time. And all these left deep join trees do need to consider all the join orders and join methods. It's not enough to say, I'm going to join A and B. You have to talk about how you're going to join them. Are you going to use Grace hash join? Are you going to use sort merge join, block nested loop join? We need to think about all of that. So this is a schema that we're going to use for our examples today. Same thing as Monday. It's, you've got sailors and you've got reserves. For reserves, each tuple is 40 bytes long. There's 100 tuples per page, and there's 1,000 pages. These numbers are going to be important, so I strongly recommend you write them down or remember them very well. For sailors, each tuple is 50 bytes long. You're going to have 80 tuples per page with 500 pages. And we're going to have 10 unique ratings. And there's going to be 40,000 sailor IDs, 40,000 SIDs. Okay. So really quickly, how many records are in sailors? The answer is 40,000. 40,000 SIDs, SID is a primary key. Typically when things are phrased like that, you want to take a look to see what's the primary key, how many unique values of them are there. Okay? Now before I talk about the optimization itself, we also need to discuss this thing of a physical property, which is something that can't be expressed in the relational algebra. If a table is sorted, I can't really express that sorting in relational algebra. That's a physical property of a table. Same with hash grouping. Okay, and some operators are going to produce these properties in your output. So index scan will result in a sorted output. When you sort a table, obviously the result's going to be sort, and when you hash a table, it's going to be grouped, right? And the similar records are literally going to be close together. So you can think of it as like that's why it's a physical property, right? Or in sort, when you sort a table, you're actually going to have the records all stored in sequential order. So that's why it would be called physical property. Now some operators are going to require these physical properties at input. An example of that is sort merge join. In order to actually do a sort merge join, the table needs to be sorted. Rather, a merge join requires assorted inputs. The merge phase of sort merge join would require a sorted input. Okay? What else? Well, we also know that certain operators can preserve these properties from the input. INLJ, for example, that would preserve the sorted order of the outer input as well. Okay? Okay. What are some physically equivalent plans? So in order to talk about query optimization, we need to talk about what plans are equivalent to each other. And what that actually means is really they need to have the same content, they need to result in the same physical properties. Here, for example, you can see if I'm doing sort merge join and Grace hash join, well, the output here is going to be sorted on SID, sort merge join. In Grace hash join, it's not going to be sorted, but if I add in a sorting step after the join, well, my output is going to be the same in both the cases. Okay? All right. So let's talk a little bit about queries over multiple relations. And really that means, what are we actually going to consider in this optimizer? So like I said, we're only going to consider left deep trees. That's might seem like a dumb heuristic, but the truth is, if you don't do that, your search space starts to blow up very, very fast. Okay? So we want to find a way to restrict the search space. We might not be able to find the optimal join, but we can at least get close enough. And the only way we can get close enough is if we pick a small subset to search through and then just pick the best out of those. And generally that'll give us a good enough answer. Okay? So left deep trees are going to allow us to generate plans that are basically fully pipelined. Okay? They're going to allow us to generate all of our fully pipelined plans. That's not to say that every single left deep plan is fully pipelined, just that one is a subset of the other. Okay? So concretely, what are we going to do here? What are we going to consider? I think it's best shown with a diagram. So the one on the left is a left deep tree. The one in the center is absolutely not. You can see here, for example, that I'm joining A and B to the result of C, but C is on the outer one here. And then D is the inner join that's joined together and result of joining A, B, and C. So visibly from the structure, we can see that's not a left deep join. So we're going to say, nope, that's not working. We're not going to consider that. And then the one on the right also, we can very clearly see that's a bushy tree. That's not left deep, so we can't join it. Okay? So, talking about the plan space once again very briefly, a full plan space is going to have, for a SQL query, all of the equivalent relational algebra expressions. Okay? And equivalent relational algebra expressions, again, you can use the relational algebra equivalencies that we learned over the last 2 lectures to kind of guide you in thinking, okay, well, which two relational algebra expressions are equivalent, and then you can kind of translate and look at plans and see which plans are actually the same. Okay, and then we're going to look at all types of mixes of those relational algebra expressions. Importantly, we'll probably need to prune the space. Okay? So we'll need to just say we're going to consider a small subset, and that's good enough for us. And we're going to try to have a couple of extra rules here. We're going to push down selection and projections always. And we're going to avoid Cartesian products, if we can. Sometimes we might have to just do a cross product, and if we have no other way. But unless we really have to, we're going to do everything in our power to avoid Cartesian products. Okay? And you might remember from the last lecture, this would mean, for example, if I have A theta join B, theta join C, that's going to be taken over A cross join C, theta join B. It might turn out that A cross join C, theta join B is actually more efficient, very rarely, but occasionally, but we're not going to consider that here, just because we don't have the time to consider all of that. We need to limit our search space. And now importantly, along the way, we're going to need to also think about physical properties like sorting. Why is that? Because although sorting is costly, sometimes if we have an order by in our query or a group by, that might actually matter later on down the line. So we might say, okay, well, hey, sort merge join is like a little bit more costly than block nested loop join. But, I mean, we're going to have to sort it at the end anyways. So is the cost of sorting in sort merge join going to be cheaper than the cost of sorting it at the end? Sometimes the answer is yes. And so in order to be able to consider that fully, we need to make sure that we actually consider and store these things called interesting orders. And I'll talk about that more in a little bit. Okay. That's a lot of talking, and bluntly, I I go over those slides because some people like seeing them written out. I really never preferred learning like that myself. So if you fell asleep over the last 15 minutes, let me sum it up. Okay? All right. I'm tired of standing. I'm sorry. I'm going to sit down. All right. So before we move on to the next step, think about these three things. Firstly, how are we going to search the space? Okay? And if you paid attention over the last 20 minutes, you can fall asleep for 2 minutes now. It's okay. All right? So firstly, how are we going to consider what we're going to search? It's way too big of a space to search, so we need to actually limit our search space to be significantly less in space and in size. That'll get us good enough to where we want to be. The way we're going to do that is left deep trees only. Okay? Secondly, we need to figure out a way to do cost estimation. We're going to have to develop all sorts of stupid heuristics that really seem dumb but actually work really well in practice. You'll see just how dumb in a second, and I'm not exaggerating. It's the type of things you'd expect a 10-year-old to do, but as is often the case in research, the dumbest ideas work the best. Okay? Lastly, we're going to need to also consider things that will help us later on down the query. Okay? And what I mean by that is if something is sorted or if something has an interesting order on a column that we're going to use later on down the line, well, okay, maybe we should consider that. Even if it's not the cheapest, we might do that earlier on, just so that later on down the line, we'll save on something like an order by clause. Right? We won't need to sort it at the end because it's already sorted for us. Let's talk a little bit about cost estimation. Okay, for each plan, in order to compare which plan to take, you need a way to physically say, well, this will take X IOs, this will take Y IOs, and then you can kind of pick between the two. So how do we estimate the total cost? Well, we have to estimate the cost of each operation in the tree. And that depends really on the sizes, the input cardinalities. Okay, and we've already talked about this for a lot of operators. We've talked about it for sequential scan, index scan, joins, et cetera, et cetera. So hopefully this isn't too new. We're also going to need to estimate the size of the result for each operation in the tree because that is going to determine the downstream input cardinalities. Okay? So we're going to have to use information about the input relations to compute what the size of your output result is going to be per operation. Okay? And we're going to do something here that may or may not be correct always, but for our sake, it works fine. We're going to assume independence of predicates for selections and joins. Okay? We're going to kind of assume fields are independent of each other. Is that actually a correct assumption? Probably not. Does that work fine? Yeah, it does. That's what we care about. Okay? And in System R, the cost is going to be boiled down to a single number for each plan, consisting of the I/O cost plus the CPU factor times the number of tuples. We're just going to worry about the I/O cost mainly, because that's really what we care about. But it has these two components to it. Okay. So we're going to have to reference that catalog that I talked about in the first QO lecture. And what does that catalog typically contain? It contains this thing called the statistics and then for each of these fields. So you're going to have like the number of tuples, the number of pages. You're going to have like the highest and the lowest value, hopefully. You're going to have the number of keys sometimes. You're going to have the height of an index if it's an index. You would hopefully have the number of index pages if you had an index. Okay? But really, all that is to say, the catalog just stores a whole bunch of metadata about the thing that you're referencing, whether it's an index, whether it's a table, okay? By the way, if you didn't know what cardinality meant, it's up there. It's okay, when I took the class, I kind of forgot what it meant too, so. Okay? This catalog is going to be updated periodically because, as we know, you can insert and remove from tables. So the tables are going to change in size from time to time. Similarly, indexes might change in size from time to time, but it's something that we're going to just update periodically. Okay? You can't keep doing that every single update, or every single delete. So we're just going to kind of do it from time to time so we never really fall too far behind. Okay? It's all right. Anyways, all we're doing is approximating a whole bunch of times. What's one more approximation really going to do? Okay? So now comes a little bit more of a mathematically involved phase of this lecture. So generally, the way to say it is the max output cardinality is going to be the product of your input cardinalities. Okay? And each term, each predicate is going to have a selectivity factor in it. That selectivity factor will tell you how much you reduce the size of your table. Okay? The way to look at selectivity is you can kind of see, how would you compute selectivity? You look at the output, the size of the output, you divide that by the size of the input. So if something cuts down a table by a factor of 10, that means the output has 1/10 the number of tuples that the input would. If anyone reads the textbook, the selectivity is actually called reduction factor, RF. I think nowadays RF means something different to a lot of us, especially over the last 2 weeks. But in the book, it means reduction factor. Okay? Now, one quick thing to bring up. When I say something is highly selective, that might mean something a little bit different from what we're used to. Okay? Here, a highly selective thing means you have a very high selectivity. It's not filtering out too many things. In English, highly selective is kind of what college admission letters like to say when they explain your rejections. Okay, so what's the result cardinality going to be like? Well, it's going to be the maximum number of tuples times the product of all of your selectivities. Okay? So like I said, we're going to assume independence of predicates. So because of that, if I have two different columns, I can kind of or two different predicates on two different columns, for example, I can just multiply their selectivities to get the resulting selectivity of applying both of them. Okay, and that's the estimation that we're going to use today. Okay, if you're given the number of keys on a column and you have an equality, so you're going to have like the column is equal to some value. Let's say boat.bid is equal to 5, and we have 100 BIDs. So the selectivity is going to be 1 over 100. Okay, and hopefully that's intuitive. If I have column 1 is equal to column 2, what am I going to do? Well, the selectivity then is going to be 1 divided by the max of the number of keys in the first column and the number of keys in the second column. Why is it max? We'll see it later on a slide with bunnies. I like bunnies, okay? I mean, they're pretty cute. Okay. Lastly, if we have something like an inequality predicate, like a column is greater than a value, you can kind of think of it like this. Remember when I had that .SID, or Sailor's.rating is greater than 5? Okay, if Sailor's.rating is greater than 5, well, what exactly is that implying? I have 10 ratings. It means I'm taking half of my ratings. So that's basically the formula that you would use for it. Okay? All right, now one last really stupid but really important thing. If you don't have any of these stats, if you can't compute it, if you don't have the number of keys, for example, if you don't have the high or low values, you're going to assume something really dumb. You're just going to say the selectivity is 1/10. That sounds really dumb, but it actually works really well. If you don't have the stats, default to 1/10. Sometimes it's very close to accurate, sometimes it's not very close to accurate. But remember, we're trying to eliminate the plans that take you from San Jose to Berkeley via Salt Lake City. We don't really care about the plans that are going to take you, we don't really care about differentiating between plans that will take you from San Jose to Berkeley via Hayward or via Millbrae. For those of you not from California, those are cities in the Bay Area too. Okay? So let's talk a little bit about selectivity estimation a little bit more deeply, and let's go through some examples. Okay? So here's some bunnies. We didn't actually need bunnies here, but I like them, so they're going to be there. Okay? Let's say you have 100 bunnies, and you're trying to compute the probability that the left ear's color is going to be equal to the right ear's color. And the colors for each ear come from two different sets, left ear colors and right ear colors. Okay? Left ear has 2 distinct colors, right ear has 10 distinct colors. What's the probability of matching ears? Let's compute this. What's the probability that the left is equal to the right? So you can kind of sum it up as a probability that any of these elements are going to be equal to each other. The probability that C1 is going to be equal to C1. C1 on the left is going to be equal to C1 on the right. C2 on the left is going to be equal to C2 on the right. Okay? Now, because I only have 2 colors for the left ear, what's going to happen? Well, I'm going to say, okay, what's the probability that I draw the same color for the left ear and the right ear, the first element? It's going to be 1/2 the probability that it picks C1 there, times 1/10 the probability that it picks C1 in the right ear set. Okay? And then I'm going to repeat the same thing for C2 because there's another color in the left ear set. And there's only 2 colors in left ear, so that's where my computation stops. Okay? So that ends up being 1/10, which ends up simplifying to 1 divided by max 2 and 10. Okay? So just remember, if you're doing something like that where you're trying to find 2 values that are equal to each other, you use the rule of 1 divided by the max of the number of values. Okay? And if you don't have that information, you're going to have to use 1/10. Okay? Okay. Now let's talk about histograms. Histograms are really cool. They also happen to be a pain in SQL homeworks. Sorry. That was there even when I was a student. I didn't like it myself, the 4.2. But when I was head TA, I got rid of the SQL, Dijkstra SQL question. So, you know, it wasn't as bad as it could have been. Okay, so. Is everyone here now familiar with what a histogram is? Okay, great. So, let's assume we kind of have like a histogram of sorts of our data. And if we do, that actually really helps us because we can construct much more sophisticated and specific estimates. That allows us to account for non-uniformity in data. So let me go through some examples. Let's say you have a disjunction. Okay? Let's say I have, that just means an or predicate. Let's say you have in one, P is greater than 99. So people that eat more than 99 potatoes per year. Or in the other column, you have people whose age is less than 26. So the query is asking you to return everyone who eats either at least 100 potatoes a year or is younger than 26 years old. So what do we do here? We know that you can't really assume uniformity in age. And you definitely can't assume uniformity in the number of potatoes consumed per year. So we're going to use a histogram to compute some information. You would basically sum up you would use a histogram to kind of sum up the number of people that satisfy the predicate on the right and the predicate on the left. And then you would multiply the selectivities of the two. Not multiply, add. But you can't just add them because then you double count. So there's this thing called the inclusion-exclusion principle. Do folks remember that from CS70? It's P of A or B is P of A plus P of B minus P of A and B. Okay, we're going to use that here. You have the selectivities of both. So what you're going to do is you're going to add up the selectivity of both, and then you're going to subtract the product of their selectivities. What that results in here is 50% plus 46% minus 50% times 46%. And that will result in a 73% selectivity. Okay? So let's concretely talk a little bit about how we compute selectivity with histograms, because I think that kind of talked about how to do disjunctions, but it didn't really talk about how we actually got any of this information for 50% or 46%. Okay, so let's take this predicate of sigma of P is greater than 99. Who eats at least 100 potatoes a year? So you have a histogram here. When you're given a histogram, which has the counts and the bin values, you will have, by nature, by definition, you are also going to have the total number of entries in the data set, correct? So what you're going to do here is you're going to sum up everything in the buckets that satisfy the condition, and then you're going to divide by the count. Okay? And here, just trust me here on the fact that the sum of these counts is going to equal 50. I know it's kind of hard to see when you're looking at the slides, but the sum of these counts is going to equal to 50, so you can kind of just trust that. And then you'll divide by 100, because that's how many rows there are. What if age is less than 26? How does that work? So here we have something a little bit annoying. I have buckets of bin widths of 5, 10, 15, 20, 25. But I asked for everyone less than 26. So what do I do here? Well, what I'm going to do is, see, I have to then spill into this bin of people between 25 and 30, right? People who might be older than 25 but younger than 26, people who are in their 26th year of life. So what am I going to do? I'm going to sum up 5, 10, 15, 20, 25. In those buckets, I'll sum it up. And then what? Then we're going to say, okay, let's have a uniformity assumption in that bucket itself. You know, we know our data isn't uniform, but we can only cut it down to some level of granularity. At some point, we're going to have to say, okay, in this part, it is, you can kind of assume uniformity in this small bucket. It's kind of like if people want to think of it like calculus, you don't have to, but if math is your thing, if you want to think of it like calculus, it's kind of like how you would approximate a function through a bunch of straight lines that are kind of, right, a bunch of tangent lines kind of approximate a function in a sense. Okay, I had 3 people being like, oh yeah, that makes sense, and then a bunch of people were like, what? So don't worry about it. Okay, so what would I do here? Well, I'd say, okay, I'm going to assume a uniform distribution within each bin. That is to say, between 25 and 30, you are just as likely to be between 25 and 26 as you are between 26 and 27, or 27 and 28, 28, 29, 29, 30. Okay? So each of these each of these vertical slices will be the same. So a fifth of the population of that bin, 25 to 30, is going to have age less than 26. Okay? Does that intuitively make sense to folks? So you're just going to add that all up, and then that's your selectivity. Okay, what if I had a conjunction there? If I had a conjunction, it's much simpler. You're going to assume age and potato consumption are independent, and you're just going to multiply the two. So your selectivity here would be 23%. Okay? So selectivity of disjunction, as we went over, it would be like this, just in case people didn't get to copy it down. No, I think everyone seems to have gotten it. Okay, great. Okay. So the selectivity for more complicated queries can kind of be thought of in a similar way. I'm not going to go over too many of them in detail. They'll be on the slides in case people want to look at them in more detail, but the extrapolation process is really quite similar to what we've gone through here. Okay? Really don't overthink it. It's mainly just common sense data. Okay? So like if you have a histogram, you kind of already can calculate by yourself, you know, what percentage of values are less than a certain number, what percentage of values fall in a range. Right? You would kind of use the same principles to calculate some of these more complicated queries. But one thing I do want to go over is join selectivity. Okay? Joins are not a special case here. I know normally we say, oh, joins are kind of special. They're not here. Just like everything else. Because remember from relational algebra, what is a join? It's a cross product and then a selectivity predicate is applied on it. So if that's the case, then, I mean, this isn't actually anything special. The way to compute this is just applying the selectivity predicate, applying the selectivity to the cross product. And the way you compute the size of a cross product is to multiply the number of tuples in each table. Because a cross product, by definition, is just every row of one table paired with every row of the other. Okay? So, similarly, you'll just, if you were trying to use, you remember our previous query had the predicates P and Q. If you were going to do that, you would basically just calculate the cardinality of R and the cardinality of S, multiply them together, and then apply the selectivity filters, multiply the two selectivity filters onto the cardinality product in order to get the size of the output relation. Can folks kind of indicate how they feel about this so far? Okay. So I'm going to skip past the column equality slide for now, mainly because I don't think that adds anything really new to the lecture. I'll go over it more later if we have time, but it's really just a similar extrapolation, but you weight it by histogram bins. It'll be there on the slides. If people want, I can go over it after lecture, but I'm going to skip past this part for now so we can talk a little bit more about what's to come. Okay? The upshot of this lecture is basically I really need to make sure that everyone here knows how to compute selectivities for basic predicates. Okay? We walked through some examples here. If you're familiar with those examples, if you can do those examples, that's very good. Okay? Know how to do it for the original Salinger version, know how to do it for the histograms. Okay? We're going to make a couple of assumptions here that we need to carry forward. Okay, assumption one is that histogram bins are uniformly distributed. Or within histogram bins, values are uniformly distributed. That's our first assumption. Okay, so if you have a range in a bin, the fraction of the range will just be the fraction of the count of the values in that range. We went through it, for example, with the age example. Okay, assumption two is that the predicates are independent. So and you would multiply the predicates, or you would sum them up and then subtract the product. And then for not, it's just 1 minus the predicate selectivity. Okay? And lastly, just remember the joins part. Cool. So let's talk a little bit about actual QO now that we have all of the tools that we need. So there's two main cases we need to consider. We need to consider single table plans and multiple table plans. Okay, single table plans are going to really include select, project, and aggregations. Okay, and what you kind of want to do there is you want to consider every single available axis path. Okay? And then you're going to choose the one with the least estimated cost. Remember that your selection or projection is generally done on the fly as we go, but really the key thing to remember, the important thing to remember in all of this, is that if you can remember that single table queries involve select, project, and aggregation, that's what to take away from here. Okay? Now often that selection projection, which is done on the fly, that is going to then be pipelined into your grouping or aggregation. So that's just something to keep in mind for how we kind of save time, save costs. Do folks remember pipelining from 61C? Similar logic here. Okay, as soon as you get some results, you can feed it into the aggregation. For example, as I'm outputting rows, if I'm doing a sum, you can kind of just feed each row into the sum operation as it comes. That kind of make sense? Okay. Okay, so let's talk about some cost estimates for single relation plans. Okay, so there's three cases I want to go through here. Case one, you have a primary key. You have an index on a primary key. The selectivity there, because primary key means uniqueness, is just going to be, or the cost there for axis rather, not selectivity, the cost is going to be the height of the tree plus 1, and that'll get you to the leaf node. And then if it's alternative 2 or alternative 3, you're going to have plus 1 to actually read the data itself. Okay? The second case is a clustered index. If you have a clustered index, what does that actually mean? Well, let's assume it's clustered and it's not on a primary key. So your cost is going to be the number of pages in the index plus the number of pages of matching results times the selectivity. Okay? What if you have a non-clustered index? What's that going to be? So remember from my B plus tree lecture when we said we had gone through B plus trees and we had decided that for clustered indexes, because of the way that the data is laid out, you would have 1 IO per matching page of results. For unclustered indexes, you're going to need to have 1 IO per matching tuple. Okay? So for non-clustered indexes, you're going to have the number of pages plus the number of tuples times the selectivity, and that will tell you really how much you're reading. Okay, and then lastly, the sequential scan of the file is just going to be the number of pages of the file itself. Okay? So, to be clear, if it's the first case where you just have a primary key, it's height plus 1 if you have alternative 2 or 3. Number 2, number of pages in the index plus the number of pages in the table times the selectivity. Okay? Really important there, make sure you know that. Number of pages in the index plus the number of pages in the table times the selectivity. 3, non-clustered index matching selection. Again, number of pages in the index plus the number of tuples in the table times the selectivity. That's the number of IOs. Okay, and those are the assumptions we're going to use. So, Now let's walk through an example, right? If we have an index, for example, on the rating, so what's this going to resemble? Let's say we want to do this query, s.sid from Sailor's S, where s.rating is 8. So what do we need to know here? What do we need to know? Do we have an index on rating? Okay, so let's say we have an index on rating. What's the cardinality going to be? The cardinality, rating is not a primary key. Okay, one thing to remember as we go through all of this. What's the cardinality going to be? Cardinality will be 1 divided by the number of keys in the index times the number of tuples in the table, and that will give you 1/10 times 40,000 tuples. Okay, that works out to 4,000 tuples. If we had a clustered index, the cost is then going to be the 1 divided by the number of keys, which is 10, times the number of pages in the index plus the number of pages in the table. Okay? If we have a 50-page index and we have 500 pages in the table, then what's going to happen? It's going to be 1/10 times 550, which will be 55 pages retrieved. Okay? What if it's an unclustered index? Unclustered index, same calculation, 1/10, but you're going to add in the tuples instead of the pages. So it's going to be 1/10 times the number of pages in the index plus the number of tuples. You can pretty easily see how this becomes really, really bad, because now your cost is 4,005 IOs. And then you also need to do the cost of a full scan. There, you would just have to retrieve all the file pages. And funnily enough, that's actually very nice here, because you just read in everything, and that's actually somehow cheaper than reading in everything in from the index. So sometimes file scans can be cheaper than index scans. Okay? So what if we had an index on SID instead of rating? Because right now I've gone through the case of we have an index on rating. What if we had an index on SID? Well, if we had an index on SID, we'd actually have to retrieve all the tuples in the pages if we use that index, because our filter is on the rating. So we need to retrieve all the records anyways, and then we need to apply the filter as we do that. Do folks kind of see why? Okay, I see a couple of lost faces. Give me a thumbs up if you understand why you would have to read everything. Okay. So what's my filter on in this query? Someone say something. What's my filter on in this query? Rating, okay? If I have an index on SID and I wanted to use that for this query, can I actually use that index to filter anything out? No. So what would I need to do? I'd actually need to use that index just to fetch all of my records. So I'd actually have to do a full scan using the index. And then I'd apply the filter. That's kind of useless. So do folks see where I was going with this? Great. Now let's talk about enumeration of left-deep plans. So how do left-deep plans really differ? They can differ in a variety of ways. The order of the joins, firstly. Okay, secondly, the access method for each of the leaf operators. How are we going to access that? Are we going to do an index scan, a heap scan? What are we going to do there? So that could also differ. We could also have different join methods for each of the join operators. So the relations could be in a different order, or I could have different joins, or I could just, literally have different ways I could scan the relations. And all of those things would make those plans differ. We're going to enumerate them using n passes if we have n relations joined. Why? Because at each pass, we're going to add on one relation. So in pass 1, you're going to find for each relation the best one relation plan. Basically, you're going to say, let's just start with this table as our root. What's the best way to scan this table? What's the best way to read it in? And maybe, apply your filters or whatever you need to do. And then, in every subsequent pass, you're going to find the best way to join the result of a plan that joined I minus 1 relations to one more relation. Okay? Now, because this is a left deep tree, remember that the outer relation will be the bigger set, the I minus 1 tables. So you can think of it as like the left is the outer in this tree. Okay, so for each subset of relations, what are we going to retain? We're going to retain the cheapest plan overall, plus the cheapest plan for each of the interesting orders. Okay, that's a new phrase. What do I mean by interesting orders? Well, keep that in your mind for a second. I'll come back to it more later on, but basically, like I said, sometimes an output is going to be sorted, and that could be good for us because we could use it later on down, maybe in a sort merge join or in an order by for the result of the query. So sometimes you might say, hey, well, doing an index scan, probably more expensive than doing a heap scan, but something I've noticed is this query requires you to sort by that column on the index. So maybe I'd want to do an index scan here and compute the estimate if I access this table with an index scan, and I'll see, is that actually cheaper than doing a heap scan and then sorting it at the end? Okay. So this is the core behind what this left deep plan and dynamic programming stuff that I've been talking about really comes down to. It's called the principle of optimality. It basically says that the best overall plan is composed of the best decisions on the subplans. So the best left deep plan to join A, B, and C is one of the following three. The best way to join A and B, join with C. The best way to join A and C, join with B. Or the best way to join B and C, join with A. And this is really important because now we can just optimize a plan by saying, okay, well, let's kind of just take the best, let's just consider how this table is, how costly this table is when I join it on to a smaller set. I don't have to worry about, for example, how A and B are joined together because I'm just going to assume, oh, I have the cheapest way to join them together already. Let me now join C onto that. This might seem kind of weird, like why are we talking about this? But think about it this way. I could join A and B using, say, block nested loop join or a Grace hash join. Okay? And actually, let me describe it a better way. Okay? Let's think about how to join A, B, and C together. I could join C, A, and B, or A, C, and B, or A, B, C, or B, A, C, et cetera, et cetera. But if I'm using dynamic programming, if I'm joining C with A and B, I'm already kind of saying, hey, I don't need to worry about which one is the outer relation on A, or on A join B, or which one's the inner relation. Okay, instead of considering both of them, I'm just going to say, I already calculated which one's the best for that, so I'm just going to tack on C to this. So I don't have to worry, for example, about join ordering. I don't have to consider A join B join C or B join A join C. I'm just going to say, well, whichever one was the best between A join B and B join A, I'm using that and then joining C on top of it. So does that kind of make sense as to why this is useful for us? Okay, so basically what that means is when you start optimizing higher level plans, you can actually reuse the best results of the subroutines. So this is how the algorithm really looks. Okay, you're going to have the best subplans built bottom up. So on pass 1, you're going to find the best plans of height 1 in the left deep tree. And then you're just going to record them in a table. In pass 2, you're going to basically join on one table onto each of those single axis plans. And then you're going to see, okay, well, I've combined a plan of height 1 with a new table. I have a new plan of height 2. And you're going to basically calculate the cheapest way for each pair of plans. Okay? So you'll have, let me give you a concrete example. You have A and C, right? I have single table axis for A, single table axis for C. Now, the most efficient way for A join C will be, should I join C onto the single table axis plan for A, or should I join A onto the single table axis plan for C? Okay, and you repeat this up until you get to pass N, and by that point you'll have combined all N tables together and your joins are complete. And so this is kind of what that dynamic programming table looks like. You have your subset of tables, this is your key, your subset of your tables in the from clause, and the best plan for it and the cost. Okay? I'm sorry I haven't stopped to go around for questions today because we just had a lot to go through so far and I wanted to get through everything so people could do their project, but I'll stay for as long as needed afterwards to go through any questions people might have. Okay? So, like I mentioned, I just want to go through interesting orders again briefly before we walk through a proper full example of this. Okay? And what exactly are interesting orders? Well, like I said, it's whether a relation is, or whether a plan is going to be like sorted on some output you might use later on. If that happens, we might want to store the result for it. Okay? So for each subset of relations, we're going to retain the cheapest plan overall plus the cheapest plan for each interesting order of the table. Concretely, a way to think of this might be, let's say I have A join C, and my resulting query needs to be ordered on A.SID. So I might want to store, for example, the cheapest way to join A and C, and the cheapest way to join A and C that results in a sorted order on A.SID. So that's really what interesting orders mean. And how interesting order is defined is basically anything that we can use later on in the query, like order by, or group by, or join attributes of yet to be added joins, because you can use sort merge join. And if you guys remember, what was really the bottleneck with sort merge join? It was the sorting phase. Well, if a table is already sorted, I don't need to resort it. So if my output is sorted on something, then I can say, oh, hey, cool. Well, if I'm doing sort merge join later on, and I have this output sorted on a column that I'm going to need to use later on in a join attribute, well, this is really good because I would be able to have a really cheap join later on down the line. So you kind of store this as an interesting order. Okay, just on interesting orders, can the class vote? How do you guys feel with it? Thumbs up, down, sideways? Okay, guys, a little bit more participation, please. Okay, so most people seem somewhat okay with it, so I'll move on. So this is, now let's extend our dynamic programming table a little bit. We're going to have the subset of the tables in the from clause, okay? We'll have the interesting order columns. It's still keyed on the first column, but we've added another column. We've added the interesting orders. I'm going to keep that here. Okay? And then you also have the best plan and the cost. Okay, now, I said one of the rules we have is we're going to avoid Cartesian products unless we absolutely need them. Okay? So, how do I consider what plans to add? Well, if something has a Cartesian product, I'm going to try to avoid it. So I'm only going to consider a plan match if there's a join condition between the two pairs of relations that I'm joining, or all the predicates in the where clause have already been used up, and I have to do a cross product to complete the join. Okay? So again, the main rule here is only do cross products if you really need to. Then after that, we're going to handle order by or group by or aggregates as a post-processing step. Okay? Now, here's the thing. This is still exponential in the number of tables. We've just taken it from very, 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 very big to very, very, very big. Surprisingly, though, that actually matters a lot. Okay, so let's wrap up with a concrete example of QO. This is our query. Okay? And if you didn't understand anything we just went through, try to just watch these 10 minutes because it will make a lot more sense to you. Okay? So if you're taking a nap for the entirety of the lecture, that's okay. You can watch the rest later, but watch this at least because this will really help as almost like a summary of what we've done. Okay? So, here's our query. I'm going to leave it up there so folks can copy it down. Note something here. We have hash and B plus tree indexes on SID for sailors. For reserves, we have a clustered B plus tree on BID. We also have just a B plus tree on the SID. Okay? For boats, we have a B plus tree on color. Okay. So, what does our pass one look like? Our pass one says, let's take the best plans for each relation. Okay? For sailors and reserves, we might do like a file scan. We also need to consider that we have a B plus tree on reserves.bid, which could be an interesting order. Or we have a B plus tree on sailors.sid, which could be an interesting order too. Why is it an interesting order? Anyone want to say? Right. Basically, it's an interesting order because you're going to maybe use it later on down in a join, right? There's a r.bid is equal to b.bid as a condition to join r and b. There's s.sid is equal to r.sid as a join condition. So these B plus trees, when you do an index scan on them, are actually going to result in a sorted output. So we're going to keep those as interesting orders. And then for boats, we have a B plus tree on color. So, you know, that might be good for us too. Because we're applying a single filter of, you know, b.color is equal to red. So hey, maybe that might be good because that would help us really cut down on the number of tuples. So this is what our DP table would look like. Okay? It's keyed on the tables from the from clause. You have your interesting order columns, and then you list the best plan for each of them. And you would need to estimate the cost, which we will kind of skip by today because that's just a lot of selectivity estimation, which we already walked through. Okay? Now, pass two, what's going to happen? Well, for each of the plans in pass one, just to say for each of the single table scans, okay, what's going to happen? We're going to iterate through every single table that we might join that's not in the plan. So for example, for sailors, we'd iterate through boats and reserves, right? And now for each of those tables, what are we going to do? So we're going to say, well, we're going to add on this table to that plan. We might, for example, add on boats to the reserves plan. What happens here? We're going to look at each of the access methods that we have stored. Okay? You can see here the plan for the access method. We're going to look at each of the access methods, and then for each of the join methods that we could have between these two tables, we're going to generate a join. By generate a join, I don't actually mean you're going to perform the join. I mean you're going to estimate the cost of the join. Okay? So here, this is a concrete list of what we would do. We'd first file scan reserves, which is the single plan. That's the outer table. We're going to check the cost of joining that with boats as the inner table. Okay, reserves is the outer table, with sailors is the inner table. Okay, and you can kind of see here we're basically iterating through each of these plans and we're adding on a table. Okay, so it's basically every single one of these rows, every single one of these entries, you're adding on a table to that. And you're going to retain the cheapest plans for each pair of relations order key. Okay, this is really what I want to get through to everyone here. If folks understand this, you guys will be fine. Okay, so now let's look at what might happen. So pass 3 and beyond, what's going to happen here? We're going to use our pass 2 tables as the outer relations, and we're going to generate plans for the next join in the same way as we did in pass 2. Just add on a table to what's in pass 2. For example, we could say, hey, do a sort merge join using the plan that has the sort merge, using the B+tree axis on boats.color and the reserves file scan. Maybe let's, let's do a sort merge join of those two with sailors. So to be clear, can anyone say, what is the outer relation in this pass 2 plan? Guys, anyone? Okay, outer relation is the result of the sort merge join between B+tree scan on boats.color and the reserves table. Okay? Inner table is going to be sailors. Axis B+tree SID scan. Okay, that's just one example. And you would kind of have this process repeated for pretty much every single pass 2 plan with the missing table added on. Okay? After you do that, now you've joined all 3 tables together. Now you're going to add the cost for your group buys or your aggregates or whatever it is, and then you're going to choose the cheapest join. This is where interesting orders come into play, because if it was already ordered by something, if it was sorted by something previous, like a sort merge join, then I don't need to actually have a separate cost for sorting at the end. So, okay, after that, you're going to just choose the cheapest plan. Okay? So that's a lot we went through today, and I understand it can be a little bit dry. So if I had to distill what we learned today down into a few sentences, it's not a replacement for lecture, but if I was to do that, let me try. Okay? Selectivity estimation I already summed up in a couple minutes. I'm just going to talk about this. Here's the way to think about query optimization. You basically say, let me just assume I have I-1 tables joined together. What's the best way to join one more table to this set? And then, now you have a series of sets that have of I tables, right? And you're basically going to say, well, for each set of I tables, what's the cheapest set that I had joined? For example, AB join C, AC join B, and BC join A. All of those are now going to be sets of A, B, C. So you pick the cheapest one of those 3, and you would say, okay, well, that's the cheapest way to join A, B, and C now. Now I'm not going to worry about how each of those were joined individually in between them. I'm just going to assume I have the cheapest cost for them now. Now let's move on. Let's try to join another table on it. Okay? So, you're going to build one in your project, okay? And you can also influence optimizers if you really want, because the truth is, There are ways to custom optimize SQL optimizers in industry. Some people don't like doing this. Some people say it really shouldn't be done. Some people do it anyways. You might choose to do that if you decide to work in this field.